two ways this mixed derivative gets made. That's why the factor of 2 is in there. It just comes from working it out. My homework assignment would be go from here to there. No problem. And dropping this term is the paraxial approximation. It's saying there's no backward propagating light. You're just ignoring that. So you could not do this at solid density, but up to really high density it works really well. And this is on the full laser field. So now this is the equation that we're left with in time, this time where we're moving along with the pulse at the speed of light. Now we Fourier transform with respect to t prime, and we get the equation that I've been showing you all along. So we get something that's d by dz, and then we have an omega that comes from the d by dt prime. We still have our transverse derivative, we do that exactly, and we have our polarization in however much detail we want to put it in. Your polarization here could be just something your friend told you, could be the strong field approximation, or could be from the Schrödinger equation, as good as you want to do it. Whatever it is, that's what's going to allow you to go. So you get a tool, which is a numerical nonlinear medium, which goes basically like this. You send a pulse in, you calculate the TDSE at one layer of atoms, you calculate the source term in that layer of atoms, you propagate that to the next level, to the next layer, using the Maxwell wave equation, and you keep doing that over and over until you get to the front of it. So let me see if I can push the button and make that happen again. So you march through layer by layer. In each layer, there's a bunch of atoms. You pick a bunch of them, maybe 50 of them that are laid out. You calculate the TDSE for each of them. You get the polarization from that. So here are all the atoms in one layer. I picked 50 or 100 of them. I farm those out to 50 or 100 CPU cores. I solved the Schrödinger equation in hopefully under 10 minutes, as it turns out. That's sort of a figure of merit. Then you get back, and you just march through the gas. And so the problem breaks up very nicely. In the radial direction, we have a layer of atoms where we're solving an independent TDSE for each of these. So this is done in parallel. And then once you have the solution for one layer, you solve the Maxwell wave equation, you march to the next layer, and that's cheap. So you have expensive, cheap, expensive, cheap, expensive, but the expensive part is parallel. So there you are marching through the gas. Now we have all the needs, back to the experiment. So the experiment in 2001, they say we're going to do carrier envelope control, we're going to pick the right phase, we're going to get only one pulse, and that works. And here's the experiment that was published in That Looks Like Science in 2004, where they did this. They had CEP control, and they measured the, they used the XUV light to measure the IR laser oscillation. So the fact that they can measure this IR laser oscillation perfectly like that tells them that they have just one pulse. Their prescription worked. It's really great. The problem is it's not 2001. So what happened in 2001? Did they not make a single attosecond pulse? So here's the first isolated attosecond pulse, and this is Henschel et al. This is Ferenc Krause's group in Nature in 2001, and the experiment works basically by the prescription that was given. They have, here are the steps that go through their experiment. You have a gas jet, you focus in a laser. In there, then a whole bunch of radiation is produced. There's a bandpass filter here, which is something that selects off just the highest frequency radiation. This is actually a mirror, but anyway, it's a mirror that reflects only high frequency radiation, and it absorbs low frequency radiation. So it's a bandpass filter. And then they do a delay in focusing, and they do a measurement. So here are the steps. The laser comes into the gas jet. The emitted XUV is rejected off a mirror that it should be reflected. The emitted XUV reflects off a mirror that selects radiation around 90 eV. That is refocused into a second gas jet. and they do a streaking measurement of the emitted photoelectrons. You'll find out what streaking is the next time Paul talks. You'll know everything about streaking. But the point is, in a streaking measurement, you know how many pulses you have. Okay? And they look like they had one pulse. Here's the problem. It should not have worked. Okay? It should not have worked because the pulse they were using is too long. It wasn't a 1.5 cycle pulse. It was at least a 3 cycle pulse. So there's many, many returns. Not many, but several returns. So the pulse is too long, and crucially, the carrier envelope phase was not controlled. So most of the pulses that they sent into the light, right? When the carrier envelope phase is not controlled, it means if you send in, hundreds of thousands of laser pulses, the carrier envelope phase is just going to be a random variable that goes all over the place, right? And so if you have just one special carrier envelope phase, which is going to produce one single attosecond pulse, and all of the other carrier envelope phases, or many of them, don't do that, they produce 2 or 3, then you're not really going to make a measurement that shows you that you have a single attosecond pulse. It shouldn't work. So, let me, give the spoiler alert. It does work. I mean, they're not kidding. They did have a single attosecond pulse. The question is why and how, and the answer is that the simple recipe is not what the physics followed. It's a coupling of space and time and ionization. So let's go back again. The pulse is too long, the phase is not controlled. Now here's the data. The data out of this experiment is really good. So here is the measurement by the single attosecond pulse of the laser light field that had emerged from the gas. And this laser light field has an identifiable frequency, which is quite different from the frequency that got sent into the gas. What went into the gas is a 750 nanometer, 7 femtosecond pulse with an intensity, if there was no gas there, of about 9 times 10 to the 14. And what they measure, looking at these oscillations, is they were able to back out by a streaking measurement, which you will learn about, that they had isolated 630 attosecond pulses at a central frequency of about 90 dB. Now there's another interesting thing that you learn looking at these oscillations of the laser field which has gone through the gas, is it has a very large blue shift. The frequency has been changed by about 35%. It has blue shifted down to 620 nanometers or something. It's an enormous blue shift. And this is obviously the result of rapid ionization dynamics. So the question then occurs, what else is the rapid ionization dynamics doing? We know from this huge blue shift that there are rapid ionization dynamics. Something is happening. So the large blue shift was our starting point, because the blue shift is caused by the rapid change in the free electron density, which is something we can deal with. So here is our numerical nonlinear medium calculation of what happened in that experiment. So you have to bear with me here for a minute. Here is a time axis in a moving coordinate frame, right? Moving at the speed of light. So here is a frozen light pulse. I know you can't really do this, but here it is. So you're looking at the light pulse that's going into the gas, and you're looking at it in time, so this is along the propagation axis, and this is perpendicular to the radiation, to the propagation axis. So this is the intensity profile of a focused laser pulse. It has the amplitude goes up and down, so when we square that, we get envelopes that go up and down, and you see as we go off axis, the intensity falls very quickly. So this is the pulse that goes into the medium. This is the pulse that comes out of the medium, and actually here it is. It is very, very different. It has been reshaped in a big, big way. You can see that now most of the big intensity peaks are actually happening off axis and in different places, and there's just a few high intensity places left on axis. And more than that, if I can make this happen again, you're going to see the movie happening here The reshaping actually happens in the first half of the medium. And in the second half of the medium, basically, it stops changing. So we're about halfway through, and then the time propagation goes on and on and on. But you don't really see this change anymore. So here's what we said happens, and I think generally they agree with us. Parents and Reiner were very, very helpful in providing all the data for this experiment. So here's your initial pulse going in. You have a neon gas. What happens in there is very rapid ionization, and the driving pulse gets really reshaped in this very funny, odd-looking thing. That even though it has lots of peaks, most of them are off-axis and in very rapidly changing spatial positions. So as a function of propagation distance, what we see is first, we see the laser intensity on axis starts high, but then drops rapidly. This is the defocusing. So the intensity drops rapidly to some sort of, something around a few times 10 to the 14. And the frequency of the laser is rapidly blue shifted. We would say about 22%. So don't exactly match that 35% number, but that doesn't take into account chirps and things. Anyway, so we get this rapid blue shift, and this is about halfway through the medium. Things have settled down. So here are the steps that we think happen. The blue shift builds up rapidly in the first half of the gas, while the intensity is still high. Defocusing reduces the on-axis intensity, consistent with a 90 eV cutoff, by the way. If they'd really put in 9 times 10 to the 14 all the way through the gas, they would have gotten harmonics out to 200 eV. They didn't see that. The highest harmonics they saw were around 90 eV. And slightly different laser focusing produces the 35% frequency shift. So, I mean, it depends exactly on how you do the focusing, how big a blue shift you get, but you get a very big one. And here is the harmonic yield around 90 eV. You see that the 90 eV harmonics are all generated in the back end of the gas. The gas density is very high. 90 EV radiation that's made in the beginning of the medium gets reabsorbed. So it's only the stuff in the back end of the medium that gets made, that gets out of the medium. And that is made not by the pulse that's sent in, but that radiation, that 90 EV radiation, was made by this reshaped, funny-looking pulse. It really has only basically one peak on axis. So here is the radiation that comes out of the gas for a given CEP phase, a random one. And you see what you get is you get one pulse on axis, some little side bands, and you do get other attosecond pulses, but these are off axis. And if they're off axis at the end of the gas, they're going to be even more off axis after you propagate for a while. And that is what they did in the experiment. They took the radiation, they propagated it for a while, they bounced it off a mirror. The mirror is very small, so it selects only the central part of the radiation, and that was refocused. So here is, for example, in our calculation, here's a very, very messy output with many different attosecond pulses in here, right? Consistent with the fact that the experiment shouldn't work. If you propagate it out 1.5 meters, put it on exactly the kind of mirror that they used and refocus it, for instance, you get 2 single attosecond pulses. But these pulses have different divergences. And if you move the mirror back a little ways, like 3 meters, then you're only going to select one of these pulses. And long story short, this is how the experiment was done. For reasons that, as far as I can tell, have as much to do with the layout of the lab as anything. It's 3 meters and not 1.5 meters. And it's a very happy ending because of that. So we would say that this is a spatial filter in the far field, works as a time gate, and it isolates a single attosecond pulse from many. And we find actually, here's a curve for the 7 femtosecond pulses that they were using. If you define a single attosecond pulse as to be something that has a 10-to-1 contrast ratio to all the other pulses, then we would say that you get a single attosecond pulse most of the time. That's this blue curve, and it's among the CP phases, it kicks that out more than half the time. So, and if you take 5 to 1, it kicks it out about 3/4 of the time. So, I think I want to stop here because I must have gone over time. But I hope that I've convinced you that there, to think about from a theoretical perspective, the generation, for instance, of attosecond radiation is very, very interesting. As far as I know, it's the only way to sort of separate these microscopic and macroscopic effects. And in many cases, and this is far not the only one, it's just the most fun one, you can explain how an experiment that shouldn't work actually does work. And we all know that those are the best experiments, right? I mean, that they work for simple reasons, and when you look at them in a more complicated way, they still work, but maybe for slightly more complicated reasons. So, thank you.
Questions?
Yeah.
Yeah.
So first, so there is the shaping of the pulse due to the annotation. How do you do that? Sorry, the shaping of the pulse due to annotation.
Yeah.
So you say that you got that beginning and it's pulse
Yeah.
shape, and is that does it reach a steady state?
Yes. Yeah, it tends to. When the intensity falls to where the ionization rate is not so rapid,
Right.
and so then the reshaping is small.
So they could stop because of the intensity as well.
Yes.
Could you bring the questions up here? Could you bring the question?
The question is, does the reshaping stop at some point, and why does it stop? And the answer is, if the defocusing causes the intensity to fall low enough to where the ionization rate is slow, then it stops the reshaping. But then you have what you have, right? So it gets reshaped in the first half of the gas, and then that's what's going through the second half of the gas. And because they were using a very high gas density, the radiation that's made in the back of the medium is reabsorbed in the medium. It doesn't get out, right? I mean, this is another thing we didn't mention, right? And it's also a problem with trying to get more photons by simply increasing the density, is you also increase the absorption of your radiation, right? I mean, you're making 90 eV radiation, anything will absorb that, right? Anything you have has an ionization potential lower than that, so it will happily absorb that light. So you can't just sort of crank up the density endlessly.
So you have a ton of quasi-free electrons in the system, right?
Yeah.
Do you have to worry about coulomb interactions between these guys? And if yes, does it mess up your parallel code?
Right. There's always two answers to this. So the first is no, it doesn't mess. We don't worry about it,
Okay.
and it doesn't seem to mess anything up, and life seems to be great.
Okay.
The other answer to that question is yes, of course, there must be some effect of it, and this is why I get very excited when I hear that the repetition rate of the next generation of high-intensity lasers is going to be orders of magnitude higher than what we're using, because this will allow us to get much, much better data, much more stable data, look at things in really great detail, and then we'll find out that, yeah, we were mostly right.
Yeah, no,
Right?
but I'm wondering if you think that you are right because these effects are 2 orders or 3 orders of magnitude away, or just a factor of 2.
I think it's orders of, for that one, I think it's orders of magnitude.
Okay.
And, I wanted to just show, this is sort of an example. So this is an experiment from Loon in Johan Morrison's group. This is a paper on the archive. And this is kind of a very complicated thing to look at, but I just want to make a point about details, right? So one detail that people say is, well, we only have to worry about 2 trajectories. There's one, a short trajectory that gives rise to light that's focused along the axis, and a long trajectory that gives rise to light that's focused off the axis. Mostly what happens is people pick phase matching conditions, and I didn't talk about this, that give you just light along the axis. So this is here's divergence in this angle, and here is spectrum in this angle, and they've chosen a phase matching condition where they have very well-resolved harmonics that are all along axis. So this, you would say, is sort of classic short trajectory. Here is, now they have changed the focusing conditions to where they have both long and short trajectories. So they have, for instance, for harmonics like this harmonic here, you have something that's very close to the axis and bright, which is kind of short trajectory, but you also have this piece that is very far off axis, and that's from the long trajectory. And if you have enough precision, enough counts, I think you can look within that and you can see, you should be able to see spatial interference fringes. This is what they think in Lund as well. See spatial interference fringes, which will show you the contribution of not just the long trajectory, but the longer than long and the longer than long. And now you're really thinking about very different trajectories, not something, now I'm going to do Paul's thing, right? Not just trajectories that go out and come back, but how about go out, come back, miss, then come back, right, on the back side of where they came out. And okay, for an atom this is interesting and it can give rise to interference fringes, but for a large molecule this is maybe really interesting because you leave on one side of the molecule and come back on the other, and are there conditions under which that still gives you something? All sorts of interesting effects that will come as we go from, standardly now it's about 1,000 shots per second, go to 10,000, go to 100,000. This data was taken with a laser that performs, I think, at about 20,000 hertz, but it could run at about 130. They didn't run it in that mode for this experiment. But I mean, they're getting just lots and lots of data, and the simple pictures that we're rolling out for you here with so much confidence will undoubtedly be modified, hopefully. So it's a field that I think has slowly always sort of joining with the rest of AMO physics, where precision is its goal. You know, there was a time when it was got kind of photons as its goal. Like how many could you get? And it was, you know, that phase matching. How do we make better phase matching? How do we get more photons? How do we get higher energy photons? And these are all very interesting questions, but they're not precision-driven questions, right? And then you have the rest of AMO physics, like you guys, that are really driven by precision, right? And I think, hopefully, we're joining.
Okay.
So is it fair to say that in your layers, okay, in the time scales of these pulses, the atoms are frozen, essentially, right? So you have a frozen gas.
Yes, for the generation problem, they're
For the
frozen.
thermal time scale of the atoms,
Yes.
they're much longer. And
Yes.
So
Yes.
they don't come into the play.
That's right. For the generation problem, they're frozen.
So can I now think of, but your atoms are independent particles, right? They're still frozen, but independent particles. And if I were to think of what would be the effect on the yield of these harmonic generations if the picture was more correlated? I know that your wave functions, of course, would be much more difficult to solve in these. But if they were sort of correlated, not interacting, but just simply correlated.
I don't know. I think the bigger effect is probably to take account of more electrons on the same emitter.
Yeah, sure.
Although that's something that sort of, people have looked for multi-electron effects in the emission. And, you know, there are some examples of that. But by and large, even that, which I would think would be the first level of complication that would really come into play, even that is only rarely been seen. So I think, in some sense, the level at which we're doing it, which is a single, you know, try and do the single electron or maybe the 2 electron problem as well as you can, and then couple that to the Maxwell equation and try and treat those effects. That's keeping us busy, shall we say.
Sure.
Yeah. Now, what I'll talk about next time is sort of the absorption of radiation, of XUV radiation in dressed systems. And there, undoubtedly, the movement of the atoms, although we don't treat it right now, is definitely a thing. I mean, for sure. because the emission can happen on, the absorption happens over a much longer time scale. It happens on the line, on the time scale of the line width.
Right.
So we can't sort of force that to be a frozen problem. So we treat it that way right now, but it's an obvious area for improvement. Yes?
It's a technical question. So, can you tell us how experimentalists fix and change their envelope phase? Of their attosecond.
Like do this or do that, and you'll get a better signal.
Yeah.
So you could, I mean, now, I don't know, maybe this is the turn off the camera part where I give it. I think that's not the game you want to be in. Because